Push that rock here with Simpson Math. Today I want to talk about the power of the Cartesian plane. For the first well over 2,000 years, mathematicians solved geometric problems using geometric principles. Then, around 1600, mathematicians invented the Cartesian plane, named for René Descartes. And they started approaching geometric problems using algebra. So here's an example. Here's a theorem from geometry. The midpoints of any quadrilateral form a parallelogram. So if I draw any quadrilateral, no matter how funky the shape, I find the midpoints of every side. Those midpoints will determine a parallelogram. It kind of looks true in this case. Of course, I didn't draw a very funky quadrilateral. Well, we could approach this from a geometric perspective, which is what the ancient mathematicians did, all of what mathematicians did in general up until the invention of the Cartesian plane and algebra. But with the Cartesian plane, we can use algebra to prove a theorem like that. So we can say, hey, given any 4 points, x, a, y, a, so this is just, we use x and y, not numbers, not a particular ordered pair, but just a general x and y to represent this could be anywhere. And this could be anywhere, this could be anywhere, and this could be anywhere. And that forms a quadrilateral. And then we say these midpoints, which we have a midpoint formula, which I haven't proven, but it's not too hard to prove the midpoint formula, and we could do that in some other video. But we have the midpoint formula to give us the coordinates for each of these midpoints in terms of the coordinates that they bisect. So M here is XA plus XD cut in half, and YA plus YD cut in half. That's the coordinates for M. So we get any 4 points, and we find the midpoints, and we have the midpoints here. Now, what we need to do is show that MN is parallel to QP, and MQ is parallel to NP. If we can do that, well then that's a parallelogram, and it works for any quadrilateral. So that's what we need to show. We need to show MN parallel to QP and MQ parallel to NP. So let's get the slope of MN. Well, we have the coordinates for it, and we just do y2 minus y1 over x2 minus x1, the rise over the run. Well, we get they have a common denominator in the numerator and denominator, so we can combine those fractions if we're careful to distribute the negative. So notice my parentheses, very important, very important. So I can combine this because it has a common denominator. I can combine these two fractions because they have a common denominator. Then these denominators will reduce. If you keep flip, you'll see that they reduce. So these reduce, and we're left with this numerator over this denominator, and notice this negative will distribute. So this becomes negative, and this x sub d becomes negative. And then we see like terms, ya minus ya, that goes to 0. xa minus xa goes to 0, and we're left with yb minus yd over xb minus xd. And that's the slope of mn in general. Okay, well, we need to show that the slope of MN is the same as the slope of QP if they're going to be parallel. So we do the same trick with QP. We get the rise over the run, we simplify, and it doesn't look exactly like the last one. So are they not parallel? Okay, well, let's look at that a little bit more carefully. I should have prepared these to be turned. Okay, so we have the slope of MN was YB minus YD over XB minus XD. And when we did the same trick with QP, we got YD minus YB, not quite the same, over XD minus XB, not quite the same. But wait, what if I factor out a negative from this numerator and from the denominator? Well, that changes the sign of both of these if I factor out a negative. And same in the denominator, it changes the sign of both of these. So then this can be rearranged. Negative xd plus xb is the same thing as xb minus xd. And negative yd plus yb is the same thing as yb minus yd. And of course the two negatives cancel. And so we see we got the slope of mn. So if that shows that they have the same slope, so therefore they're parallel. Now, to finish this proof, all you would have to do is rinse and repeat with the other two sides. So you see how powerful a tool the Cartesian plane can be in doing simple geometric proofs. Math made simple at Simpson Math.